Okay, it's our great pleasure to have Professor Xingting Wang from LSU to give the talk of our seminar this week. We will talk about Hopf algebras of dimension p squared in positive characteristics. Let's welcome.
Thank you, Elon, for your introduction. I'm very happy to be here, give an online talk. Actually, I'm in China now. We are in the same zone, but we are still like far away. So my topic is about some work I done with Richard Ying last year. It's mainly about classification of some finite dimensional Hopf algebras. And we are focused on the other side of the story because nowadays there are almost a big program of classifying Hopf algebra and beyond quasi-Hopf algebra tensor categories in over complex numbers. And that's very important in physics and all other applications. But I'm mainly focused on positive characteristic because that's what I done at my PhD thesis, and I want to extend this program. So let me give you some background on the main storyline about classification of Hopf algebras. So my talk will focus on Hopf algebras, but as I mentioned, there are a lot of extended works in the categorical level of different quasi-Hopf algebras. So I think you should be very familiar with the background, but as usual, I have to include the slides, like say something thing about Hopf algebras. So Hopf algebra is defined in like, century ago, mainly on topology side and the algebraic geometry side. But around the 1980s, when Drinfeld introduced his famous Drinfeld doubles, there's a deluge of applications of Hopf algebras in all sorts of mathematics, theoretical physics, especially using Hopf algebras to find invariants of knots and links in three-dimensional space, and also other area like quantum mechanics and formal field theory, TQFT. So Hopf algebra is like main machinery to run these programs. And one thing which is actually a direct consequence of being a finite dimensional Hopf algebra is its representation category carry a very fundamental structure called tensor structures. And in particular, if the Hopf algebra is semi-simple, means the representation category is semi-simple, then it gives examples of fusion category. And you can add all sorts of different structures on Hopf algebra, and the corresponding category become nicer and nicer until people can use it in a very smooth way. So that's like a main motivation why I need to learn these Hopf algebras. So let me give you some history about how this classification program, especially related to my work, comes into being. So let's set up some basic notations. So K is a base field, and for the classification sake, I want K to be algebraic closed. It's not a big deal, but to make calculation a little bit nicer. And I focus on positive characteristics, so I pick my favorite prime P. And some number theorist friends warn me that 2 is not a welcome prime, so you can take P as greater than 2. So starting with 3, 5, anything beyond 2. And H is denotes a finite dimensional Hopf algebras over the base field K I picked up. So the story about thinking about these problems, like what kind of Hopf structure we can have in a particular dimension, start with Kapelanski's conjecture in 1975. It's actually at the back last page of his book called Bialgebra. So he's at that time, there's the Hopf algebra like just came into being. Sweedler defined what Hopf algebra is, and people trying to study it from different point of view. So that's where the conjecture comes into our site. So so it's mainly based on characteristic 0. Then if you take a Hopf algebra in dimension P, then it should only give us the classical case, which is a group algebra. So Kaplansky, it took a few, almost 20 years to solve his conjecture, and is eventually solved by Zhu Yongchang in 1994. And I'd like to summarize some of his main ideas. So it used some results which are natural extensions of results we know for group algebras. So it's come from the classical group theories. Is we have so-called Nichols-Zula theorem, says every group algebra is free of the subgroup algebra. And that works for Hopf algebra too. And also we have a so-called Swidler force formula describing the force power of antipode. So using these two tools, we can prove that if you are in carrier P in characteristic 0, you have to be gonna have a semi-simple Hopf algebra. And also the main contribution of Zhu Yongchang did at that time is to generalize a classical result of GIKs on category rings of semi-simple Hopf algebras. And deduce from this kind of like irreducibility condition, he can prove that it has to be a group algebra. Now things become a little bit involved when we taking dimension jump from P to P squared. Here we still assume we are in the more commonly accepted field characteristic 0. And it's in 1996, Mazurka proved that if H is semi-simple, adding the semi-simple condition, then H still has to be a group algebra. So nothing new will happen, just the classical group picture. And at that time, it's almost 30, I think almost 30 years ago, that at that time, that except the semi-simple case, in all the Hopf algebras in dimension P squared, which are not semi-simple, are only known as Taft algebras. So that's the Taft algebra become more and more known in that place. So what is a Taft algebra? So let me quickly review in case you don't know that. So let's take an integer n, and omega is a primitive nth root of unity. So the Taft algebra defined by Earl Taft, which is the advisor of my collaborator Richard, defined it as a algebra which has two generators, x and g. And g is play like a group-like element. So g to the power n is 1. X is like a skew primitive element. So n's power is 0, and where the two generator omega commutes, you swap the position, they differ from a scalar omega. Then it's the algebra representation. Being a Hopf algebra, you gotta have something more. So you have a here I use the delta, mean the co-multiplication. You can split elements. So G is be like a group-like, X be like a skew primitive, and also the antipode and the co-unit are defined along the way. So also has some well-known facts, which is kind of like standard, but good to know, is in the language of co-algebra, we have a definition called pointed, mainly refer to the co-representation category to having a simple object of dimension 1. So in that sense, the Taft algebra is pointed. And the order you can check easily is n squared, and the antipode squared has order n. And also, if you restrict your integer n to be 2, and this omega has to be -1, you get a so-called 4-dimensional Swidler-Hopf algebras. And that is known to be the smallest Hopf algebra, which is not the dual and itself is not a group algebra. So that's where the Hopf algebra picture really differs from the classical group case. And that's the smallest dimension you can have. So now, after this definition, Susan Montgomery made the following question in several international conferences, asking whether Taft algebra are the only non-semi-simple Hopf algebra in dimension P squared. And Richard in 2002 gave an affirmative answer to Montgomery's question, and that's his approach. So you start with a P square Hopf algebra, and we don't want semi-simplicity, so it's non-semi-simple. Then you can use the similar Swidler S4 formula to get the power of S4 is P. Then the trick is to consider the trace of the 2P's power of your antipode. And he showed that this trace is an integer divisible by p squared. Then, using a larger Raffer result, because if S squared is identity is semi-simple, we are not in the semi-simple case, so the order of S squared has to be a bigger than 1. So you can deduce the order of S squared only can be P. Then you apply a earlier result of Andrewskiewicz and Schneider to conclude the result. And that's basically what Richard showed in his work for proving Montgomery's conjecture. You can see that. And if we summarize all we know in this case, and it's all happening in characteristic P, for dimension P and P squared, we have the following complete picture. So you only have 4 classes. The first 3 are the group case, which says we have the classical group regarding the Hopf algebra. And the last one is the Taft algebra. And Taft algebra has a parameter omega. So in each dimension P squared, you have P minus 1 choices. And we can show they are not isomorphic using indicators. So they are generically not the same. So you have P minus 1 non-semi-simple ones. Then we move to another story. That's the main topic today. So now we want to do the similar thing, but we are trying to change the characteristic from 0 to P. Now, one thing we should be aware of is many things behave quite well in characteristic 0, become bizarre or weird when moved to positive characteristic. Like using the Mascule theorem, right? A group algebra over C, a finite group algebra over C is always semi-simple, but if you move to characteristic P and P divides the order of your group, you're gonna have a modular representation cases. So sorry, So we expect things become a little bit blur in this case. But also for the sake of knowing things and also for some representations, now they like support the variety theorem, Balmer spectrums, people like to do things in carry P and the number theory. So it's something we like to know, but we're expecting the classification will be much richer and might be difficult to conquer even in these easy dimension PP squared. So we get almost the same setup, except P has also being the characteristic of the field. Then we had our first result I with Richard in 2019, says that you have the following cases. There are 3 cases in total, and the first case is exactly the same. Only difference is this time the characteristic P divides order, so it's a modular case. You have infinite many irreducible, indecomposable. For P maybe, yeah, but the representation category is a little bit different. And for the next 2 cases is totally new. And that's the picture will come again. So it's good to think about it a little more. So we have 2 more new family of Hopf algebras. And these Hopf algebras are coming from Lie series. So the co-multiplication of the generator X there just means in Hopf algebra call them primitive elements. Remember in the Taft algebra case, the generator X is called a skew primitive. Here we call it primitive because you have trivial group like, right? X tensor 1, 1 tensor X. And these things in finite dimensional case only occur in positive characteristic. So there is the result known by I think is earlier that if you have primitive elements, then you have to have infinite dimensional Hopf algebra. Only in characteristic P, they can happen in finite dimensional case. So these 2 and 3 are exactly the examples of that phenomenon. And I want to say a little bit about the proof. So actually the proof is quite different from Drew's proof in carry 0. We don't use the character ring series because it's a modular case. We don't have semi-simplicity. So what you really do is also first taking care of the order of the antipode. It seems like a very natural way to think about the antipode first. And also there's a categorical way because antipode refer to some traces like diagrams. The other one is we look at a representation theoretic approach to H. We actually estimate the dimensions of the indecomposable projectives over H. And since H is dimension P, that becomes a little bit easy. So we show that in this case, H is either local, means has a one simple module, or dual of local, we call the connected coalgebra. So the co-representation has one simple objects. So that's how we get these three families in characteristic P. Now, there's another conjecture which I like to say, but we don't have much good result on that, is when you let your dimension be a prime, characteristic field be a prime, but they are two different primes, right? That's the most general case. So we take a Hopf to be dimension Q and a closed field, base field K of characteristic P. And we know when P equal to Q, it's just our previous classification. But what about P is not equal to Q? So our conjecture, or based on what we know, is that we conjecture if the characteristic is not equal to the dimension of the Hopf algebra, then it has to always stay to be a group algebra. It seems like a natural conjecture, but it turns out super hard to prove. So what's the idea is we know some boundaries of these condition holds. So we can use Eddinghoff-Galacki's lifting theory. Means if both semi-simple, co-semi-simple, then no different from the character zero, we can show the conjecture is true when Q is smaller than P. And we vary that if Q is a little bit smaller, like Q is smaller than Q is a little bit bigger, but smaller than 4P, then we use the idea of analyzing the group-centric rings of the small ranks to show that it's also the case. And also this bound between P and Q was further improved by Eddinghoff using some ideas in the integer Z plus rings. But other than that, I think the problem is quite open. And we believe, Rich and I all believe that you have to have some new techniques in modular representations to deal with that. All the thing we can do is push bound, but to completely solve it needs a complete new idea. So we don't know that. And now that's all the picture in character P in dimension P. So let's do the similar extension, right? We put P to the power square. And we ask the same question, what kind of thing we have in carriers P. And that's actually an early work we did in 2014. We call that result of W squared, because both of us has last name start with W. So usually I say W squared result. So we add one more condition to H. Assume H is pointed. So as I commented before, point means the co-representation category is has all irreducibles dimension 1. Or you can say the dual Hopf algebra is a basic algebra. Then we have these cases, which we completely classified. So it has to be either one of these classes, group algebras as usual, and we'll have Lie theory kick in, restricted universal enveloping algebras, and you can take duals, vector space duals. And also you can take tensor products. And we have one special family left. It's called the Rutherford algebras. And before I move to the Rutherford algebra in details, I'd like to make another comment to that. We use the argument of Andrew Skiwich and Natali earlier by counting the dimensions in lower degree. Basically, we take the corradical filtration, counting the dimensions, and show that this is the case. So let's move to the Hopf algebra. I talk more in today's talk is the Rutherford algebra, RP. So the P denotes actually the same as the characteristic of the base field, and is a P square Hopf algebra. So it has two generators, like in the Taft case, XG and GP is 1, and the relations of X changes. So in the Taft case, which is in characteristic 0, X is nilpotent operators. Here, XP is X, so it's a semi-simple operator, and the relation between XG is given by the third line in the relation space over there. And the co-multiplications is very similar. G is group-like, X is skew primitive with a similar antipode and co-unit formula. Okay. And there are some facts about the Rutherford algebra over there. First is, that's also a story I like to talk about. It's about Hopf algebra. So when Swidler defined the Hopf algebra, people have no idea what is antipode per rule. Not like today, right? We have more graphical tensor category explanation of how the trace of antipode controls the whole thing. But at that time, people have no idea how the antipode play rule. So even, early people think the antipode order has always to be a bounded number, like S squared is identity. But this is the first example given by Rutherford, for 50 years ago, that you have a Hopf algebra whose order of its antipode can be arbitrarily larger, right, like 2p. So that's why the Rutherford algebra was defined. And also Taft denote that RP is the extension of the group algebra, and its antipode is not a semi-simple operator, which are all brand new at that time, 50 years ago. So Richard actually, when he saw the work we done, the square work we done, he asked the following question many times, and I like to put it in the question mark because that's the main concern. My remaining talk is, if you take what Taft algebra is unique in the world of carrier zero Hopf algebra in dimension p square, that's how the RP should play his role in the positive characteristic world in dimension p square Hopf algebras. So the question can be formulated in the following sentence: is RP the only non-commutative and non-co-commutative Hopf algebra in dimension p? And then some quick comments as how this will actually complete the classification story. So first, we know all the point ones, right? As I said, we classify them. So compare our nodes, we can see RP is the only non-commutative, non-co-commutative ones in the point one. So that's true for the point ones. And also, if that question is solved, then actually we classify all the p square dimensional Hopf algebra, because if you are a commutative and co-commutative, it has to be pointed or dual pointed. So if that's the only exotic Hopf algebra there, then everything else is pointed or dual pointed. So that's also like consequence of that will complete the story of the classification. So now, before we get into some detail of the techniques, I'd like to summarize some of the main results. Actually, the paper is online. I forgot to talk about that. You can search probably the same title and contains all the detail if you like to know a little bit more. But I can summarize pretty quickly in the following few slides. So K algebraic closed carries characteristic P square dimensional. Then we have the following equivalent statements. First is basically characterizing what Hopf algebra inside this p square dimensional Hopf algebras. First is H is isomorphic to the Taft one. Second, H is pointed, non-commutative, has a non-trivial group like. H is non-commutative, and it emits a normal Hopf subalgebra, which is a group algebra. And the fourth equivalent condition is it fits into a extension of two p-dimensional Hopf algebras. And its non-trivial extension means you're not having simply tensor product of two, but you have like a clef extensions, which you have mingled algebra and co-algebra structured by some co-cycle conditions. So we couldn't prove the entire conjecture, and turned out much harder in at least we believe it's a little bit harder than the carry zero case, but we have some results approaching this question. So that's the first characterization. Then comes the second characterization. So we have the similar conditions. Then we have the following cases when we can prove Rutherford is the only non-commutative, non-co-commutative. First is if you look at all these p squares coming from extensions of p1s. Second is if we know H has a non-trivial group like. So you have a subgroup inside. Third, it seems like a trivial thing is if you have primes smaller enough. Smaller enough, I mean, not in the sense of a number theorist, because small means billions, millions. We cannot do that. So we only can do p less or equal to 5. And everybody can count the number. You only have three main primes to concern. But to us, it's like, it's actually the hardest case to prove. So we are, and I'm going to explain how to achieve these three conditions in later slides. And we have some more results I like to say before we jump into how to prove how to the general strategies. So let me introduce some examples of p-squares in more detail. So here is another Hopf algebra from the Lie series. When you want to have the Lie bracket playing rule, you have to stay in characteristic P, because otherwise you take about infinite dimensional Hopf algebras. So this is the two-dimensional Lie algebra. And when you have Lie algebra in character P, there's an additional structure called a P-restricted map. It's basically, if you look at a G embedded in the GLN, it's P's power of the matrix. You have all the axioms which give you what P-restricted map should be. So easy way to understand it is just taking a 2x2 matrix, taking P's power. That will be the P-restricted map. So if you stay in the two-dimensional one, and that's a non-abelian one, the bracket x, y is y, you have two P's power maps, mapping x to x, yp to 0. And in this case, we can form the so-called restricted universal enveloping algebra. So what is it? If you didn't hear that, it's very easy to explain. So you forget about the restricted Lie algebra part. So you have an enveloping algebra of the Lie algebra. And that's infinite dimensional one, which we don't care about in our talks. But you can make it a finite dimensional, just like the small quantum groups, right? You're supposed to model out some central elements. Now, the central elements you model out come from taking the P's powers of the generators of the Lie algebra element. So you model out xp equals x, yp, then you can show it boils down to a finite dimensional Hopf algebra. And the co-multiplication is xy both primitive. So one consequence of that is actually prove that the Rutherford algebra can be obtained from Lie series restricted universal enveloping algebra by a twist, by a Drinfeld twist. So let's consider the Drinfeld twist in the UG expressed in the following way. So you have expressions I, the index I, if you look at the box over there, from 0 to p minus 1, you take the one. And that's an actually invertible Drinfeld element inside the UG tensor UG. And you can twist the UG by this Drinfeld element. Now, the consequence, you're going to have a non-commutative, non-co-commutative Hopf algebras. And what we do is we prove that the RP, the Rutherford algebra, is exactly this. So in the tensor category language, we just say the RP and UG are gauging equivalent. We know UG is a braided Hopf algebra with the trivial braiding. So a consequence of that is the rep RG is the symmetrical braided tensor category. So actually, the Drinfeld element J is actually given earlier by Galacki, and it took us a lot of time to actually prove it's a Drinfeld element. So the reason is P can be arbitrarily bigger, right? So if you check the condition, it's probably like devastating. So actually, the way we can show is the Drinfeld element, you have to use model P result to cut from the quantum group case. Then you take everything in some integer closure of Z, then you mod P. Every coefficient divided by P disappear, and that's one left. So that's the way, the only way we know how to show is actually a well-defined Drinfeld element. So that's another field comes, so the next result is we show that another characterization by normal Hopf subalgebras. So we show that if H admits a normal Hopf subalgebras, then if and only if H is pointed, and we show that every pointed p-square dimensional Hopf algebra come from extensions, This result is well known in the group case, right? If you know P squared is abelian group, it has to be an extension. But in the Hopf case, the extension need not to be trivial. Like or in the P square case, you also have a non-trivial one. The cyclic group of P square, you're not gonna have a two cycle twisting that. But in the Hopf algebra case, you have more non-trivial extension from P square Hopf algebras. And that's the last one. So the last one is actually we classify all the possible extension from the P dimensional ones. So I have to introduce more examples, and these are summarized in the first few lines of my next slide. So first is the restricted Lie algebras. So what we did is the A1, A2 in the first line is one-dimensional restricted Lie algebras. Now, one-dimensional Lie algebra, the bracket is 0 because you only have x. The only thing different from them is the restrict map. So you can map x to a semi-simple operator to itself or map into a new opponent operator. And that's the only two one-dimensional restrict Lie algebras. And the next, for the GIs, I have G1, G2, G3, G4. These are the two-dimensional abelian ones. So the Lie bracket is still 0, but since you have two elements, you have more choice of the restrict map. And up to a classification, we can show there are only 4 of them. And the last one, we already showed that in the Radford twist result. But, oh, sorry, jump a little. So, so that's, we name it called the G5. And also there's another one, the fourth one coming from the group scheme. The P squared finite group scheme is this one. So what we do is we can summarize all the non-trivial extensions. And there are only 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Nine of them. And the middle one is how the extension would be. Now, if you look at, there are 2 rows which says that no trivial extensions. It's from UA1 to UA2 or from UA2 to the group algebra CP. So non-trivial means every extension you fit there, you're going to get a split extension. Means the middle one is a tensor, basically tensor of the 2 ends. And all the other one you have the non-splitting extensions. And the Radford is exactly one of them from CP to UA1. UA1 is the due of CP. So it's, as Taft mentioned before, it's extension from CP and its due. So what we did is we classify all the possibles. And through this list, we can show the middle one are all pointed. So that's how we prove the extension are all pointed ones. So that's all the result we get so far. So now I will spend, let's see how many. I think I'm fine. So maybe the next 15 or 20 minutes to explain a little bit more about the terminology and techniques we use. Hopefully it will motivate you how to apply these ideas in the more general setting, right? Not only carries P, maybe you can do some categorical thing. That's also our hope. Our result transcends from the world of Hopf algebras. But I will try to be a little bit specific, so let's only focus on the algebra side. So first is give you a quick reminder what extension of Hopf algebra would be. So we know extensions of groups, right? You have a normal subgroups, and then you have the quotient group, and the middle one is called extension. Now this thing happens for Hopf algebra as well. So if you have 3 Hopf algebras from K to A to H, when we say A is the extension of KH, mainly we mean the following 3 things hold. So first is K is a sub-Hopf algebra of A. And not only sub, but the normal Hopf sub. So we can define the normality exactly. We define the conjugation action of groups. So K is invariant under the conjugation of A. Using the conjugation is defined using antipode. So it is basically a mimicking of what conjugation of group actions is. So K is a normal subgroup of A, and H is a quotient of A by K. And the quotient ideal is actually K, that's a third condition, K plus times A. And if you translate everything in group, it exactly means K is a subgroup of the group algebra A, and the quotient group is H. So it's a natural generalization in the group case. And what we show is that some representation properties are invariant under such extensions. So that's the three conditions we prove. First is if K is local, then H is basic. I mean, all the representation are one dimension if and only if the ending point L is basic. If L is connected means co-representation is basic, right? Then you can conclude K is pointed if and only if H is. Oh, connect is more than that. Connect means it's local, dual local. Sorry, I correct myself. So connect means as a co-algebra representation has one simple object, the dual version of local. And pointed means dual of co-representation is basic if and if H is pointed. Okay, so that's how we get from extensions. And now I want to explain a little bit about how to cook up the extension by cohomology theories. So this is a pure generalization of the ideas, how the group cohomology play in role inside understanding the group extensions. We know that the Hochschild, I like to use the Hochschild, they are same, but the Hochschild, H2 of the Hochschild representation of the group controls the group extension. So in the Hopf case, we can do the similar case, but we cannot do for every Hopf algebra. So we need some assumptions. So that's the right assumption, and that's actually done by Sweden. So we have to start with the co-commutative Hopf algebra. And if you really like characteristic 0, you already drop out of the race because every co-commutative Hopf algebra has to be S squared identity. So it's a semi-simple one. So mainly it concerns in positive characteristic if you do extensions, because if you in the semi-simple one, the group cohomology will vanish in degree 2. And A has to be a commutative algebra with the right action. The right action we call it H module algebra structure. We don't need that in detail, so I just say it. And also you have the Hochschild complex. Here Swidler use the name reg H2A. So what are they? So these are all convolution invertible maps from n-fold tensor of H2A. So here there is a convolution invertible. So what it does is I'm not like the Hochschild complex, like taking all the k-linear map from H tends n to A. Actually, I'm taking A as an algebra, n-fold tensor of H as a co-algebra. Once you have a linear map from a co-algebra of algebra, you can make the whole set, home set, into algebra. And the convolution invertible just means the unit elements in the algebra. So that's the subset of linear maps. And you can define a so-called co-simplectual complex on this by consider these co-faces operators. And the definition is very similar when you use these simplectual complex in Hochschild cohomology. But the only thing that the addition in the Hochschild complex becomes multiplication under the convolution product. Other than that, everything is basically the same. So I will just say it without mentioning more. And once you have a simplex complex, you can take the differential. And the nth differential is called a Swidler cohomology of H with coefficient in A. It's literally kernel partial derived over the image. And here the partial is given by these co-phase operators. The only thing that in the Hochschild, you add minus them. Here you times and divide them. So here the star means multiplication using convolution product, and F inverse means the convolution inverse. Here's the only thing that you replace addition by multiplications. And you can show that this will give you the a well-defined cohomology groups called Swidler cohomology. So the other thing I should say before I state the next result is that the second term of the Swidler cohomology controls all the extensions from A to H. So if you have a middle term between A and H, how can these extensions be is controlled by this S Swidler 2. So what we did is we compute in some cases what the second Swidler cohomology would be. So that's the case we consider. So we let K to be algebraic closed field, carries characteristic P, we let H to be a dual of an elementary abelian groups P. So you take G as abelian P groups and take its dual. And one thing I like to mention is not like the characteristic zero case. This dual of an abelian group is not isomorphic to itself. In carrier C, they're isomorphic by characters, right? So taking dual of abelian group, we don't change anything. Elementary abelian groups, but here H is totally different thing. That's very important. And also I take NA as a commutative H module, commutative ring with an H action, and I want the invariant ring. So if you have group action, you have the invariant ring fixed by the group element. If you have a Hopf action, you can cook up the similar definition called the invariant ring of the Hopf action. Okay, and I want the invariant ring to be complete local ring with relative field K. So take some limits. Then we can show using Henson's lemma that if you are in that case, H is a dual of elementary abelians. H could be anything, but the invariant ring has to be a local complete ring. Then the Harshal cohomology of secondary, not Harshal, sorry, Swidler cohomology of the secondary ring must vanish. Now, here the characteristic clause is pretty useful. Actually, the characteristic clause is useful in classifications and the cohomology series. So, general case, if K is failed to be algebraic closed, is given by Gillett. He showed that you have a non-vanishing Harshal cohomology. And you can, it's a good exercise to show if K is algebraic closed, that expression K over basic everything plus a square is actually becomes zero. So that shows that the algebraic closed condition is quite critical here. So sorry, any questions?
What lemma did you use? You use hands-off lifting?
Yeah, so the basic idea is we first prove it in the relative field K by a Bruton force calculation. Then we lift it to A because AH is complete local ring. It's p-adic complete. Then we show that if you lift it up, every co-boundary still lies in a co-cycle still lies co-boundary. That's why we use Henson's lemma. So as a consequence, we prove that we can classify the following sequence of Hopf algebras. So we use exactly the same condition as before. G prime is elementary abelian, and G is abelian P group. Then the second cohomology vanishing, and the consequence of the vanishing of the second cohomology is as an algebra, it has to be a trivial extension. So it's just a smash product of Kg with Kg prime. Okay, with some actions you have to figure out as well. But that give us a very good understanding how this algebra will be. So the basic idea is using this, we can show no matter which smash product you have, this H has to be basic. So every simples are one-dimensional. So we are basic in the case we like it to be. So that's the main idea of this, using this lemma. So the next case is when we start with H over arbitrary characteristic. V is a simple H module, and I want some subgroups of the group elements in the dual called G. So maybe I should say a little bit more about that. So if you have a Hopf algebra H, you can take its dual. The dual is still a Hopf algebra, and you can collect all the group-like elements in G star. They corresponding to the simple modules in G. Every simple module in G gave you a group-like in G star. And you take a subgroup, so you can understand as you take a subset of the one-dimensional simples in G, and the consequence is that if you tensor with V, a fixed V. Okay, so K beta is the one-dimensional simple corresponding to the group like in G star. I want this to be a subgroup as the stabilizer of V by tensoring one-dimensional simple. So that's one way I understand it. And we prove the following result. If you take the Harshal cohomology, no, group cohomology, let's say that, sorry. of the G in the coefficient of G cross is 0, then we can view this simple H module as a free KG module. So that's using some idea from Nichols algebra and the group cohomology. But the good thing of this gives us a control of the dimension of V. So that plays a role in the classification cases. So that's one of the important lemmas we use a lot to control the dimension of a simple module. It cannot be small, too small, basically idea. And the vanishing of the group cohomology happens in the following two cases, which both of them are used. The characteristic 0 is U lot. The carrier P is new. It's just we begin this work. But from 0 is well known. So if G is a cyclic group, the H2 vanish. And also by a similar argument, we can show if G is a P group, you can be any P groups in carrier P that also vanish. So that's actually the case 2 is what we rarely used here. And being a free module, we means the dimension of a simple module has to be multiple of G. So if G is bigger, then the simple dimension is bigger, then we almost know all the simple modules of H. So that's the basic idea of how to approach the classification. Now, the next result I always feel very fascinating is we have so many results in characteristic 0 about the groups. So my understanding, maybe it's not true, but my understanding is the group representation governs the representation of Hopf algebras in characteristic 0. So everything you have to use group representation a lot, even though it's not the case. But I feel like representation of group is one step to the representations, the first step to the representation of Hopf. Now, in characteristic 0, if you talk about, you are very interested like group schemes, right? Cohomology group schemes, support variety, whatever, tensor triangular geometries. Then you have to move to modular case, because where the stable category of rep is not 0. That's where the interesting things happens in that direction. You cannot ignore the rule of Lie algebra. That's something completely new, because in character 0, finite tensor category don't see the extension from the trivial modules. So having a primitive element is same as x2, the extension of the trivial module is non-zero, but it never happens. I think that's a result proved by Eddinghoff. Any finite tensor category, there's no extension between the trivial modules. But in category 0, it can be non-zero, and it's almost every time it's non-zero. You always have an extension between the two trivials. And any extension between the two trivials, you get a primitive element. When you have a primitive element, the Lie theory play into role. So that's something I feel like we have to do it, but it's not easy to do it, because we cannot use anything we know from the group theory, and Lie theory in positive character is different from the semi-simple Lie group case. So I feel like something new. So we start with the finite dimensional Hopf algebra over K of characteristic P, and we take a primitive element. Now, one thing I look at is you have extension between the two trivials. Now, what we can say about the Hopf algebra, how the Lie theory controls the representation of H, that's a bit fundamental question we want to answer. We don't do too much, unfortunately, but I think we have something we can say. And you take the C as the sum of simple subcomodules of H. So you take comodule, adding them together. So what we get is also like the boundary condition is if C is fixed by this primitive element. Now, if in the group case, you mean the character is fixed the module. Here it's the comodule fixed by the primitive element. Then we can do the similar tricks, right? Is we can show that if you let X generate a subalgebra there, remember Kx is not a polynomial ring, it's a subalgebra in H. So you have to have a relation X, which make it a finite dimensional. So the dimension square, not the dimension itself, but the square divides the dimension for each simple coalgebra there. So we also have a dimension counting argument. And that's always the case. So if C is simple, so if you take one simple coalgebras, and suppose P does not divide C, okay, so you are not having simples of dimension P or P, it have to be P squared, by the way, P squared. Then we can show the kx times C generated by C is a free module of kx of rank C. So that's the things we had. Then by combining all these things together, we have the following general result. So if we have an algebraic closed field of characteristic odd P, and H is a cosemisimple of dimension Pn, then and the group like is big enough, basically it's Pn-1, then we can prove H is always pointed. So that will eliminate the case of Radford algebra. Will give us something very good because pointed one, we know their classification and we know when they will be Radford. So that's something we done, but we do a little bit general. We take n Pn powers. Okay. So maybe I will answer the last question. I know my time is almost up, but let me answer the last question. The last question is not the least question. Even I comment that you're only 3 primes counting 2 less than 5. But I feel like doing this is still ask a lot. Maybe there should be an easy way to do it, but we cannot see it. Even doing P less than 5 takes a lot of work. So we're starting with a algebraic closed field of carries P greater than 2. Dimension 2 is easy to argue, by the way, because the total dimension is 4. I think the classification of all group or algebra is even known in dimension 4. So we don't think P equals 2 it will be a challenging thing. So and we can argue indeed. So we stay with the odd primes. And H is the dimension of P squared. So here, basically, I mean dimension 9 or 25. And what we do is we consider the representations of H, and we put out all the simple modules together and write irip H, and this is all the set of non-isomorphic simples. So we get some conditions on the numbers of simples allowed or the rank of the Grothendieck rings in some sense. So if H is not local, so it has at least 2 simples, then the rank of this one is greater than 2. So basically you have to have 3 simples at least. And if TP dimension 2, fine. So that's the 25 dimension. You at least to have 4 simples. And also we have the following result is assume we are in the weirdest case, which H and H star not pointed. That's thing we try to delete, right? Suppose we have the unthinkable thing. Then the order of S square is identity. And in this case, if S square is not identity, then we prove that H has no S invariant 4-dimensional simple subcoalgebras. It seems too much technical, but the way we do that is actually we can use an argument by Bichon and Natali to use a quantum group to play role in classification. So we take UQSL2, but the Q is not taking the roots of unity in characteristic 0 is the roots of in carry P. Then we can play the same rule to get something from the Hopf algebras. And the first part is we just did in carry P squared, but it's a natural extension we did in carry P. Just make a more boundary estimate. So I believe that's the last slide. So we do is that after using these 2 techniques, we can show if P is less than 5 and P is a P-dimensional in carry P field, then we prove that it's not possible to be H or H is pointed. Not pointed. So which means that we are in the nice cat Hopf algebra we know already. So and also as a consequence, we show that Radford is the only one, both non-commuter non-semismiple. Now, one common thing is that I believe that our techniques won't work if P is greater than 5. I have no idea. I mean, to be honest, maybe Richard has some very nice idea. To me, like I have totally don't believe how to approach this for general P. I mean, I have no idea how to prove it, but that's what we can do so far. Thank you so much.
Thanks, Xingting, for the great talk. Any questions?
Can you hear me?
Yeah, yes.
Yes, so I have a question. You talk about the lifting. You said
Mhm,
out of the Hopf algebra of dimension p in characteristic
mhm,
q, we can apply
mhm.
lifting even only if
No,
q
the
is
one.
less than p.
Yes.
I was
So let me
surprised
go
at
back.
this kind of inequality because in
Mhm.
what sense uh, p different from q? I expected that you only need p different from q. Why lifting only?
Oh, the reason is yes. So the reason is the way to apply the lifting theorem is we need S square equals identity. When S square is identity, a classical result of Swider and Radford shows that we can lift it. Now, if the characteristic P is much greater than the dimension of your Hopf algebra, you can analyze the trace of S square and formally to show that S square has to be identity. But if the dimension is much bigger than P, the bad thing that you may have blocks of P, which adding together is zero. But that wouldn't happen if the whole block of your matrix is much smaller than the characteristic. So that's actually something we think about for many times, but we cannot deduce that S square is identity. That's why we cannot use the lifting property.
Is there
Only when the size of your S square is smaller than
yeah, is there explicit counterexample where q is greater than p, where the lifting
we
is
will have no, yeah, we don't have any examples.
okay.
Yes.
Any other question? 啊，不，你就直接问中文就行了，不用管。
对，我们不好意思，对，我
王老师，我想问一下那个
嗯
关于 twist
嗯。
那个定理啊，就是那个 twist 的话，你怎么把那个 Redford RP 那个上面的代数，就是你怎么找到一个阶啊？是的，它 twist 等价 UG 阶这个过程的话，能不能再稍微透露一点？对。
对，就是最难的地方就是把这个 J 找到，
啊，
就是
对对，这就是
有两步，就是第一步 J 是非常难找到。后来我们发现，就是你用那个在那个 quantum group 情况 UQ SL2 的时候，它
对
有一个 J 的，然后你把那个 J 相对于 modular P，然后你会模到 P 上去，正好是这个形式。然后一旦你证明有这个 J 过后，下面的证明不是很难，所以你要证明两个事情，第一个就是你要证明 UG 还是 pointed。就你要证明这个 J 过后，它这个东西它还是 point。第二个就是你要证明余集过后它是 non-semi-simple、non-cosemi-simple 这两个，然后用分类，就是我们知道在 point 的情况下只有一种 Radford，所以我们就这不是一个 explicit 证明，我们也不知道怎么去找到 explicit 证明，我们是用 来证明，说我们也不知道这个 H 怎么过，因为这个公式太复杂，我们证明 J 是个 twist 都搞了半天。所以如果你要好的方法，也许我们很想知道，我们没有好的方法。
OK，谢谢，OK，Thank you。
Other question？我问几个。这个你的结论是不管在哪个 characteristic，就是只要 characteristic 不是2吧，
对，
2也可能也行，就是 p 平方或者是p 或者 p 平方为的，要么是 pointed，要么是 dual pointed，对吧？
对，是，
就是所有的这个结论都是这样的，对吧？不对，就是你这个还没证完，对吧？Radford 这个还没证出来。如果 Radford 这个证完了，就是所有的都是 pointed 或 dual pointed。
对，因为如果你是交换或者余交换，它就一定是 pointed 或 dual pointed。所以如果你证明如果两个都不交换或者余交换，它就是 Rutherford 的话，那就证完了，相当于。
OK，那你觉得就是 general 的 p power 对吗？
General P power，我们
不管在哪，就是说我 character 是 p，
我懂你意思，就是 carry 不等于这个。
那character 不等于，我可以等于啊，我想想啊，这样吧，character 是0，那个 p power 就不一定对吧？对不对？
就是 Rutherford 它只能定义在 carry P 上，就是说，如果你比如说你跟就那个
我现在想说，我把这个我只关心 p power dimension 的 Hopf algebra over any field。
这种问
哦，
题
这个哦，懂了，就是你
比如说
想做
P
跟 P
power
一样
的
的是吧？
Hopf代数 over
对对
calculus
对对，
是零，是
哦，我懂了，让我
都
想想啊，
吗？这个我不知道的。
对，就是说，如果 P 等于 P，我觉得 reference 就是最奇怪一种。如果 P 不等于 Q，我觉得就跟那个 group 差不多，可能就只有 group case，我猜。
可能就是 P power 有吗？有不同的 P power 的东西吗？就是说，比如说我 calculus 是零，比如说 P 的3次方，
对，
有没有不是 quantity 也有，有没有不是 quantity？目前没有。所以我们会相信，就是说我P 3次方、P 4次方、P 的5次方这种东西，over calculus 是零，都是 quantity，有没有可能是这样的？
就是你目前我知道的是，好像都往次方，如果非半单的，可能
嗯
都是quantity的这种样子，或者是队友。
对，quantity 或队友都 quantity。
对。
就是说这个大概大家觉得这个可能是对，就是有可能有一定的可能性。
如果你能找到一个非 quantity 的队友也是非那个的话，
对，那是很好的。
变得非常 exotic。
OK，我就是这个意思，就是说你比如说calculus 里有可能所有的 P power 都是 quantity 或多 quantity，然后你
对
P 的话可能也是。
对，有可能就是你说的这连续性定理，虽然速度不是连续的，就是对，
有可能。
我们其实也是这样猜的，对，但是
然后对 OK， 然后你说这个 Rutherford 是 symmetric 对吧？
对 Rutherford 是这个
它是 symmetric 的，就是它的 ref 是这个
它是
ref
triangular Hopf algebra，triangular
对
Hopf
对
algebra，
对，
对，这也很奇怪的，就是
那他们
说，
是不是都是 symmetric？就是
对，
开
就是说，对，
说就是这样吧，开头是 P
嗯，
平方，你就算证不了这个都是 Rutherford，你能不能证明它的 representation category 都是 symmetric fusion symmetric tensor category？
呃，对你这个很好，就是说，我觉得你的猜法可能是对的，所以 P square 都是 symmetric。我们就是说，如果你
有可能是吧
away from Rutherford，其他的 braided 上我看不出还有 non-symmetric 的。但是很难，因为你算 braiding 的话，你那个我们没有具体算过，但是我相信在 P square 上可能只有 symmetric braiding。
？OK
如果你能找到一个 non-symmetric braiding P square，我觉得是很 exotic 的 case。
OK，然后我比如说 Rutherford，这样吧，就是那个 CP 它的 quantum double 在 characteristic P，
嗯，
也是这个 CP 是 CP 还是 CP 平方？
再说一遍。
就是 cyclic group P 对吧？
嗯
我考虑它的 group algebra，
嗯，
它的 quantum double 我可以做对吧？
哦，
它那
对
个 quantum
，quantum
double 是
应
P 平方
该不，如果它是 abelian group 对吧？它应该就是一个
，CP 对吧？不是 P 平方。OK，
对，
所以在这个情况下，quantum double 也是 symmetric。
对，是的。
奇怪的。OK，
就是我再补充一点，就是说，如果你看 P square 不看 P square，你看 P 好了，在 P 的情况下，它只有 symmetry，那一点现在也没有人证明。
哦，是吧？哦
对，原因就是因为 quasi Hopf algebra 没人证明，就是说你要搞到 tensor cat，你一定要做 quasi 嘛，但是 P 点面型的 quasi algebra 都没人分出来过，只有人分出 P 的就是朱永昌嘛，就
，OK，
跨地的都不好分，那你根本就不知道，所以这就是对，
OK，也合理。
对，但是我们相信应该都是 symmetric，我也觉得如果你有一个 non-symmetric braiding 会很奇怪的，
对，会比较奇怪的，是的。
对，但不知道没有反例。
OK。Other questions? Let me check. Okay. If there's no question, let's thank Professor Xingting Wang again.
谢谢。
好，谢谢。那我们今天就这样，等着以后你有时间来 BIMSA 访问啊。
好了，谢谢你，一龙，我们再见
好，
啊，
拜拜。
拜拜。